Okay, so on to the final example as far as piecewise functions. And, what we have covered throughout this, whole lesson here is piecewise functions, can be continuous, they can be discontinuous, and there's a couple different ways, right? I mean, they can be continuous as we looked in there. They can be discontinuous by a jump, by asymptotes, or by a hole, right? So what we're going to look at here is we're actually going to have some values. Now, I made a mistake here. That should not be 5. That's going to be some unknown value. Let's call that k. I use B, but it could be A, K, C is usually another common one that's referred to. But basically what we have is we have a function and we have an unknown value where B or K is going to be a unknown value. It's a real number, but it's unknown. And what we want to do is we want to find that value that's going to make the function continuous. So if one thing that we have hopefully learned throughout this lesson, that if this function is going to be continuous, then we know it's going to be continuous where the restrictions are, right? And if you look at that, like, oh, I messed that up. X is less than 0. That should be x is less than 1. Oops. But anyways, going back to this example, you can see that these functions are discontinuous at 1. These functions are discontinuous at 0. These functions are discontinuous at 0. So if this function is going to be continuous or discontinuous, it's going to happen at 2. So what we want to do is we want the output values. See here, the output values are not the same. So what we're going to try to do is we're going to take these two equations and we want the output values to be exactly the same. And so what we're going to do is we're going to plug in the x values for each of these functions and we want their output values to be the same. So algebraically, how we're going to represent that is to find the value b that makes these continuous. That means we're going to set these equations equal to each other, or these rules equal to each other. And then we want the outputs to be the same. Well, remember, the output comes from plugging in the input. And we don't know what x is, or b is. So by plugging in the input, that means we're going to get the output, and we want the output to be the same. Well, notice now we have an equation where we only have one unknown variable, which is b, and therefore now we can just simplify and solve. So 6 minus 1 equals 2b plus 7. Therefore, this becomes 5 equals 2b plus 7 minus 7 minus 7, negative 2 equals 2b. Divide by 2, negative 1 equals b. So what that means is when b is equal to a negative 1, so you can just plug in negative 1 in there, then these two graphs, if you were to graph this, and again, I didn't create a link for Desmos, but if you go into Desmos and plug these two functions in, you'll see that they are now continuous at 2. And let's just go and double check that. Let's make sure that they are continuous at negative 2, at 2. So if I was to plug in 3 times 2 minus 1, that needs to be equal to a negative times 2 plus 7. Let's make sure this works. So this is 6 minus 1, which is 5. This is negative 2 plus 7, which equals 5. So therefore, you can see that it is indeed continuous. Boon b is equal to negative 2. All right, next example. Now we kind of have two quadratic equations, a little bit more difficult to kind of understand what these graphs looks like, but we know we're basically dealing with two parabolas, one that opens up, one that opens down. We have our unknown variable b that is in different positions that we want them to be the same, but we're going to set up everything exactly the same. We're going to set them equal to each other, and then we're going to evaluate for our input and to make sure their outputs are the same. So I'm going to skip a step and I'm just going to set them equal to each other with their input values in. So I'll do b times 1 squared minus 3 times 1 plus 1 has to equal negative 1 squared minus b times 1 minus 5. Now, to kind of make sure I've covered all my work, I'm just going to kind of simplify this a little bit. 1 squared is going to be 1, so that's going to be b. Negative 3 times 1 is negative 3, plus 2 is negative 2, equals 1 squared is 1 times negative 1 is negative 1. Negative 1 minus 5 is going to be a negative 6. b times 1 is a negative b. Now what I can do is add the b's to both sides and then add the 2 to the other side. So therefore, by adding a b onto both sides and then adding a 2 to both sides using your properties of equality, I get 2b equals negative 4. Divide by 2, and I get b is equal to -2. Now, again, if we just want to verify our result, we can plug in -2 in for b, and just to make sure that works. So let's go and do it. Why not? So I'd have a -2 times 1 squared minus 3 times 1 plus 1. That needs to equal -1 squared minus a -2, make sure you're using parentheses, times 1 minus 5. All right, let's try to simplify this kind of quickly here. So this is 1, so that's a -2. That's a -3. That's plus 1. This is a -1. That's a negative times a positive is a negative times a negative is a positive, minus 5. So let's make sure these work. That becomes -5 plus 1 is a -4. This becomes a positive 1 plus -5 is equal to a -4. So therefore, we are good. That is continuous when b is equal to -2. All right. It's getting slow. So there we go. You can see my work here. All right, last example here. And so this one I accidentally wrote in a number here, but here's my k. Now, if you remember on these types of functions, this is basically a function, the absolute value function, but we just have a hole where x cannot equal 4. So if we want to find, like the way that I kind of think about this is like there's a hole like in the ship. We got to find the value when the absolute value is equal to 4 to kind of plug it in, because this graph, you know, just, let's see, shifting up to, so this graph looks something like this where there's a hole, right? And then it equals some value, you know, k. So what we want to do is we want to find the value of the function, you know, at 4 to kind of plug that in. So all we need to do in this case is just plug in 4 into our function. We don't need to set it equal to, you know, either value. 1/2 times 4 is going to be 2. So I have absolute value of 2 minus 2 is equal to absolute value of 0, which is equal to 0. So when k is equal to 0, does that make that function continuous? And again, let's, you know, when you plug in 4, that makes it 0. That would then make that function continuous. So there you go, ladies and gentlemen. That is how you determine the value that makes a function continuous. Doesn't matter if that value is b, c, a, k, or whatever else. That's at least the process. So hopefully piecewise functions now you are complete. Hopefully you feel a little bit more confident when you're seeing piecewise functions and you know kind of at least the process to go ahead and follow. So on to the next one.